Okay, here we go. Second video, kind of weird. Not really sure where I'm supposed to look. When I film these things, I tend to look at myself in the screen and not at the camera, which makes for awkward eye contact. Anyway, try to work that out. Today, Disneyland is closed for a while now. And because Disneyland is closed, they released their Dole Whip recipe. Now, if you've been to Disneyland, you know what I'm talking about. The Dole Whips there are amazing. So we're having Disney Day here. I got my Halloween Mickey shirt on, wearing my Star Wars hat, because the wife said if you want a Dole Whip, you've got to wear your Disney clothes. So we're all dressed up in Disney clothes around here, and we're chopping up pineapple and we're making Dole Whips. So, all right, here's the question for today. I think this is a really interesting question. I do it as a demo, most likely, usually in class. One of those things where we'll pose the question, then normally I'd have you guys talk about it in your small groups, maybe even have you guys do some whiteboarding, and then come back as a small or a larger group. But we don't have that luxury. So what I'm going to do is I'm just going to pose the question, and then I'm going to show you the three kind of ways to answer the question. So here we go. We've got two styles of cup or wheels or whatever you want to call these things. They do kind of model train track wheels. If you look closely, that could be a big clue. So my A rubbed up. We have cup A here, where we've got two identical cups and we have taped them together with the big sides in the middle. So we've got cup A, and it's going to roll like this. So large radius in the middle, radius decreases as we go outward. Okay? And then we have cup B. How does that work? Okay. Then we have cup B. Same cups, identical, except now they are taped in the center with the small radius in the middle, and the radius increases as we go out. So there you go. We got cup A and we got B. And what we're going to do is we're going to roll them across a meter stick ramp, or some rails, if you will. So I got our physics book. You know, this is what we use the book for, to make ramps. And all I do is I've got two meter sticks spanning from one table to the next. So I kind of have my meter stick bridge going on here. And the question is pretty straightforward for you guys. I'll tell you straight up, one of these cups will always make it across the bridge no matter what we do, and one of them will always fall off. We could propose cup or wheel C, which would just be a cylinder, and that'd be boring. So that's not that. But one of these designs will make sure that it always makes it across the meter stick bridge ramp, and one will always fall off. Guaranteed. Every time. So again, what we're going to do is we're going to have our cups, we're going to put them on the meter stick bridge, and we're going to let them go. Right? Or we're going to have cup B, put on the meter stick bridge, and we're going to let it go. And one of them will make it across, one of them will fall off. And now that's the question. Which one is which? And of course, explain why. I have three explanations, one using rotational kinematics, one using forces, and one using energy. So I guess at this point, what you should do is pause the video and go think about it. Maybe sketch out some of your own ideas. Show you the setup one more time, right? We got cup style A, gonna put on the meter stick ramp. Maybe do one of these again, right? So there's your ramp. They're parallel as I could be. One does look like it has a little bow in it. But there you go. That's our meter stick ramp. And we're gonna let each one roll across the ramp. One of them will make it, one of them will not. Which one is which? So yeah, maybe pause the video for a few minutes and think about it. And then hit continue to see the cups rolling and then my explanations. Okay, here we go. I think that's a good view of our ramps. So, kind of will give it away, but I'm going to do cup B first. So here's cup B. I'm going to line it up as straight as I can and let it go and fail. Okay, maybe I didn't line up straight enough and fail. Let's line it up a little offset. See, that helps. Nope, that makes it worse. Offset this side. Nope, that makes it worse. So cup B is not where it's at. Cup A is going to be a lot better for us. So if I line it up nice and straight, cup A has no problem getting across the ramp every time. Just to see it be a little more dramatic, we'll start it off really tilted and off to one side, and then you can see it's doing this nice swerving motion, kind of self-correcting as it goes back and forth. So there you go. One more time. Okay, so what we saw is that cup A, or set A, is the one that makes it across the meter stick bridge. Now there's three explanations for why cup A will make it across the bridge almost every time, compared to B, which will almost never ever make it across unless you can somehow get everything nice and parallel and there's no variations. So when you watch the video, cup A kind of does this wandering thing, right? It kind of zigzags back and kind of self-correcting all the time, making sure that it makes it across. So first explanation is just like some simple rotational dynamic stuff, right? The fact that the point of contact with the cups and the rulers changes all the time, meaning then the cup is rolling with a different radius all the time. So when we look at the cup, if it's tilted like this, then we've got a point of contact here on the cup where there's a smaller radius compared to on this side of the cup, which then has a larger radius in contact with the cup. So what does that mean? Well, we know that all rigid objects, when they rotate, every point on the cup is making the same radians per second, right? Every point on the cup has to make the same revolutions in the same amount of time. No point on the cup can make a revolution in different amounts of time. It's a rigid object, right? So every time cup A makes one revolution, every point on the cup has the same angular speed. So we know that omega here is the same for every point. So what does that mean then for the linear velocity at each point? Well, if you have the same rotational speed, but you're at a larger radius, then you're going to have a different linear speed. And we see that using our conversion between linear and angular speed, which is like so. So then the larger radius you have, the larger velocity you're going to have. So on this side of the cup, where the larger radius is in contact, you're going to have a faster velocity than you are on this side of the cup with the smaller radius. So what's that allow the cup to do? That allows the cup to turn. If this side of the cup is moving faster, it's going to rotate the cup as this side of the cup goes slower with the smaller radius. So this side of the cup is going faster, it turns. Now this side of the cup is going faster because now it's in contact with the larger radius, so it turns, and we see that cool kind of swerving motion as the cup goes down the ramp. And then we can see that when we're in contact here at the later points. Now we have the larger radius in contact, and this side has the larger V, and then this side has the smaller V, and so then the cup turns back again, giving another rotation. So, simple explanation with just some basic linear and rotational kinematics. Every part of the cup has the same angular speed, making the same rotations per second, but depending on where the cup is touching, you're changing the radius that's rolling, so then you're going to go faster, or you're going to cover more distance with that larger radius than you would with the smaller radius on this side, and you get that fun swerving motion. The The opposite then is true with cup B. It's always going to unself-correct, if you will. It's going to have the opposite effect. As it's tilted here, this side then is going faster with the larger radius, and it just steers itself off each time, as opposed to cup A, which self-corrects, always bringing it back to center. Okay, second explanation is with forces. So this one's kind of interesting, right? We know where the center of mass of the cup is as a symmetrical object. So we know the center of mass is here in the center of the cup. And what I've drawn here is two positions of cup A. One where it's kind of swerving off the track to, I don't know, is this my left or your right? Doesn't matter. This side, and then another showing when it's then in the other position off to the left or to the right. I don't know. The camera switches. You're over there. I'm not sure. So if we look at the normal force on the cups, we can also justify why the center of mass always goes back to the center. So in this configuration, more of the mass is over this side of the ruler, which I guess I'm going to start calling the left. So on the left side here, mass is closer to that point of contact. So then the normal force will push at a slight angle perpendicular to the cup surface, like so. So we have our nice normal force from that one. I'm going to draw that one nice and big because, well, because more of the mass is closer to that point in contact. Where over here, the center of mass is further from this ruler, so you're going to have less support or less normal force because more of the mass is further away from it or resting on this ruler. So we'll still have a normal force. It'll start pointing at an angle, but it will be much smaller than the other one based on where most of the mass is. So then you can see that if I look at my two normal forces, I also have my weight force, which is balanced out by the vertical components, but I'm going to have a bigger component to the right here from this normal force compared to this normal force from the right side. And so then overall, we've got a net force that is to the right from the normal forces, which is going to force the center of mass back into the center. But then, of course, once it gets to the center, it's going to have some velocity, it's going to keep going, and it's going to shift over into this position, and then things switch places, right? So then, now more of the mass is closer to the meter stick on the right, so we would get the larger normal force now on the right side, and we would get the smaller normal force on the left side, giving us then a bigger force back to the left, or the component of the normal force back to the left. And then that's going to make the center mass of the cup move back left. And then that just keeps taking place as we watch our cup swerve down the ramp. All right, third explanation is using energy and even a potential energy diagram or graph where we can look at what is the potential energy versus position, and we can kind of sketch that out here just based on where the center of mass of the cup wants to be. So center mass of the cup, again, it's in the center, nice and symmetrical. Now, basic rule of energy is that it wants to be in its lowest state. So we want to have the lowest amount of energy possible. So what configuration puts the center of mass at the lowest height possible? When it's in the center, right? If I'm taking my cup here, right, then the lowest the center mass can be is when it is centered between the two rulers. When it starts moving side to side, the cup kind of goes up and down in this upward parabolic motion. So if I were to track the center of mass as it swerved down the track, the center of mass would be pivoting up and then up in this direction, right? And if we look at that and we were to think about this as a potential energy versus position graph, then we would get what we would call a stable equilibrium position, right? Where in the center of the two rulers is where the lowest amount of gravitational potential energy is, And so the forces, the normal forces, like we just talked about, are always going to be pushing the object back to that lowest energy state, or at least trying to, even though it's oscillating back and forth, because it accelerates past that middle point, we get this kind of upward curve motion. So as the center of mass moves up and our cup veers to the right, then the forces push it back to the left, and then we'll overcorrect and go back over to this side where again the center of mass has risen and we've got more gravitational potential energy, and we really want to be in that middle position. So cup A's arrangement allows for a stable equilibrium position, where cup B does the exact opposite thing. As it's in this position, as it rotates over, it does a concave down motion with its center of mass. So if we were to be looking at that, and I'll draw that in red. So if we look at cup B, as it rotates, yeah, in the center is where it wants to be, but as it rotates over this way, the center of mass actually does something like that. Does that make sense? Might actually rise. Where then the positions here on the left and right are lower potential energy positions, and that's what the cup's going to want to do. The forces are going to then push it away from the center to try to get that cup center mass even lower as it oscillates, and we have what we would call an unstable equilibrium position, because now the forces are always going to be driving the cup's center of mass away from the middle, and that's why cup B immediately steers itself off the track. Right? So hopefully that makes sense. We got our explanation with energy going on here, where cup A has a lowest potential energy in the middle, where cup B, then its lowest potential energy is off to the sides. So we got a very different approach. We've got cup A with a stable equilibrium position, and we've got cup B with an unstable equilibrium position. So cup A is always going to be driving itself back to the middle, staying on the track, where cup B is trying to always then drive itself off the track. We can see that by looking at the forces, right? Where the normal force is always going to be pushing to the center, whether it's positioned to the left or the right. The normal forces are always driving cup A, center of mass, back to the middle. And we can relate that if we want to talk a little bit more math, right? We do have an equation for that, right? Which says that the force is equal to the negative derivative of the potential energy function with respect to x. So if this is my stable equilibrium position and I take the slope on the right is positive, which means the force is going to be negative, driving it back to the left, where if it's over here on the left, the slope is negative, therefore we're going to have a positive force, again driving the force or the center mass back to the middle. So hopefully that makes sense. I think this is a fun question. It's much funner to do in class as a demo and kind of watch it go on. But the three explanations are kind of nice. I thought it was a good place to start reviewing a little bit of rotation, also bringing some forces back in and reviewing those energy diagrams. So there you go. That's how cups roll.